Imagine holding a sealed container that has remained untouched for 4.5 billion years, older than the Earth, older than the Sun's first planets, packed with material from a time before our world existed. That's essentially what NASA pulled out of the Utah desert in September 2023, after a 7-year, 1.9 billion kilometers round trip to a tiny asteroid called Bennu. The mission was simple in theory: scoop up a few spoonfuls of space dirt and bring them home. But when scientists finally cracked the canister open and looked inside, they found things that, by all reasonable expectations, shouldn't have been sitting in a barren chunk of rock drifting through the void. So what was actually locked away inside Bennu? Why has it forced researchers to rethink the chemistry of the early solar system? And how did some of it survive at all? To understand why this matters, you first have to understand why scientists are so obsessed with asteroids in the first place. These ancient lumps of rock and ice are relics from before our planet was fully formed, leftover scraps from the chaotic disk of material that swirled around the young sun. They were there at the very beginning, when everything was still taking shape, which makes them something close to a cosmic time capsule. Locked inside them are the original building blocks of the planets, and quite possibly of life itself. If we can read what's hidden in that material, we can read the story of our own origins. But here's the problem. Although meteorites rain down onto Earth all the time, and we have plenty of them in collections around the world, they're compromised samples. To reach the ground, a meteorite has to scream through our atmosphere, heating to incredible temperatures that scorch and alter the delicate materials inside. Then, the moment it lands, it's contaminated by everything around it: soil, water, air, microbes, making it almost impossible for scientists to tell what was original to the rock and what crept in after impact. It's a bit like trying to study a pristine ancient document after someone has set it on fire and then buried it in mud. The only way around this is to go to the source. Collect a sample directly from an asteroid, seal it away from Earth's environment before it can be tainted, and bring it home untouched. Do that, and you suddenly have access to organic compounds, hydrated clays, and fragile substances that would otherwise be impossible to detect. And that is exactly what OSIRIS-REx was built to do. The first NASA spacecraft ever to travel to an asteroid, physically touch its surface, and carry a piece of it back to Earth. Japan's space agency had managed something similar with its Hayabusa missions, but for NASA, this was uncharted territory. Crucially, the way OSIRIS-REx grabbed its sample was extraordinarily gentle. A brief tap on the surface and a puff of nitrogen gas to kick the dust loose, rather than anything violent. Hold on to that detail. As we'll see later, that gentleness turned out to matter far more than anyone anticipated. After 7 years away, OSIRIS-REx finally came home. Or rather, it passed by home, dropping off its precious cargo on the way. As the spacecraft swept to within about 100,000 kilometers of Earth, it released the sample return capsule towards the atmosphere and fired its own thrusters to swerve clear, avoiding a collision and setting off on a brand new mission we'll come back to later. The capsule, meanwhile, had a narrow window and a precise angle to hit if it was going to land on target, a stretch of Utah desert roughly 600 square kilometers in size, about the area of the city of Chicago. What followed was 10 minutes of controlled violence. The capsule slammed into the atmosphere at a top speed of 43,000 kilometers per hour, making it the second fastest human-made object ever to enter Earth's atmosphere. Just 3,000 kilometers per hour, shy of NASA's Stardust capsule. It endured a staggering 32 Gs. That's 32 times the force of Earth's gravity. To put that in perspective, you feel a single G just standing still. A typical person blacks out somewhere around 4 or 5, and a fighter pilot in a specialized suit might withstand 8 or 9 for a few seconds. 32 is almost beyond imagining. As it tore downward, the capsule's exterior reached around 2,700 degrees Celsius, roughly half as hot as the surface of the Sun. And yet, the sample inside stayed below 75 degrees Celsius, shielded by a heat shield called pica. The way it works is beautifully brutal. As friction superheats the shield, its outer layer deliberately burns away, vaporizing and carrying the heat off with it in a process called ablation. The shield sacrifices itself so the contents survive. 2 parachutes slowed the descent, the second bringing it down to a leisurely 18 kilometers per hour, about the pace of a cyclist on flat ground, and the capsule touched down gently in the desert. A recovery team swept in by helicopter to whisk it away to a clean room before Earth's atmosphere could spoil anything inside. And then came an unexpected twist. Within a couple of weeks, scientists at NASA's Johnson Space Center popped the outer lid and found a bonus: 70 grams of dark grey rock and dust sitting outside the main canister, already 10 grams more than the mission had originally aimed to collect. But the real prize, the pristine material sealed deep inside the touch-and-go sample acquisition mechanism, refused to come out. 2 of the 35 fasteners holding it shut had been infiltrated by Bennu's own dust, stripping the threads so no existing tool could budge them. Picture that for a moment, retrieving a capsule from millions of kilometers across space only to be defeated by 2 stuck screws. But NASA engineers, being NASA engineers, they simply built a solution, a custom screwdriver-like tool with bits machined from surgical-grade, non-magnetic stainless steel, designed and tested to work inside the sealed, nitrogen-purged glove box without contaminating a thing. 3.5 months after landing, it worked. The canister finally opened, bringing the total haul to more than double the original target. And what they pulled out next wasn't quite what anyone had been expecting. Some of the very first surprises came from grains so small you'd need a microscope to see them, and so old they predate the Sun itself. These are called presolar grains, microscopic crystals that condensed out in the cold of space long before our star ever ignited. They are survivors from a previous generation of stars, swept up into the cloud that eventually collapsed to form our solar system, and they carry a chemical fingerprint of where they came from. Here is why that is so useful. The kind of elements a star can forge depends entirely on its mass. Small and intermediate-sized stars burn gently, fusing light elements like hydrogen into helium, and given enough time, they can work their way up to heavier ones like carbon and nitrogen. More massive stars run hotter and can fuse far heavier elements still, all the way up to silicon and iron. And the real heavyweights end their lives in supernova explosions so violent that they create elements heavier than iron in an instant, scattering them across space. Because all of that material eventually gets recycled into new stars, new asteroids, and new planets, reading the composition of these tiny grains is like reading a guest list of the stars that contributed to our corner of the universe. When scientists examined Bennu's presolar grains, they found evidence of small and medium-sized stars, but also the unmistakable signature of supernovae. And then came the part that genuinely caught researchers off guard. A team at NASA's Johnson Space Center discovered that these grains held roughly 6 times more supernova dust than any extraterrestrial material ever studied on Earth. 6 times. That's not a minor statistical bump. It's a strong hint that exploding giant stars played a far bigger role in seeding our solar system than we'd assumed, enriching the raw material of everything around us long before the Sun, the planets, or we ourselves existed. But the presolar grains were only the beginning. As scientists worked their way deeper into the dust of Bennu, The discoveries didn't just continue, they escalated, building towards something that struck right at the heart of one of science's biggest questions. Where did life come from? It started, reasonably enough, with the basics. Initial analysis revealed a sample rich in carbon, nitrogen, and organic compounds, exactly the sort of chemistry you'd hope to find, and the raw scaffolding from which more complex molecules can be built. So far, so expected. But there was more. Sifting through the material, researchers found 15 of the 20 amino acids that every living thing on Earth relies on. Amino acids are the components that chain together to build proteins, the workhorses of biology, and to find 3/4 of life's essential set sitting inside an asteroid is remarkable on its own. And still, there was more. They also found all 5 nucleobases: adenine, guanine, cytosine, thymine, and uracil. These are the chemical letters that spell out the genetic code, the rungs that make up the ladders of DNA and RNA. Every instruction in every living cell on this planet is written using these 5 molecules, and here they were, intact, in a rock that had been drifting through space since before Earth existed. Then it went one step further. A team led by Yoshihiro Furukawa at Tohoku University in Japan identified essential sugars in the sample, including ribose and, for the very first time ever in such material, glucose, one of the key energy sources that powers life as we know it. And there's a subtle but profound detail hidden in that result. The team found ribose, but not deoxyribose. Ribose is the sugar at the core of RNA. Deoxyribose is the one at the core of DNA. The fact that ribose appears to have been the more common of the two in the early solar system lends weight to a fascinating idea known as the RNA world hypothesis, the theory that the very first forms of life didn't use DNA at all, but instead relied on RNA to store their information and run their chemistry, with DNA arriving only later. Now, an important note of caution before we get carried away. Finding amino acids, nucleobases, and sugars inside Bennu is not the same as finding life, or even evidence that life ever existed there. What we've found is the parts list, not the finished machine. But to discover such a complete roster of life's raw ingredients, the building blocks of proteins, of genetic code, of cellular energy, all bundled together inside a single asteroid, is genuinely astonishing. It tells us that the chemistry life depends on was already being assembled out in space long before any of it found its way to a young, watery Earth. And then there was the find that nobody saw coming at all, a substance that had never been documented in a space rock before. Tucked away in the sample was a strange material that researchers took to describing as a kind of space gum, a polymer rich in nitrogen and oxygen, with a chemical structure surprisingly close to polyurethane, the stuff we use here on Earth to make foams, coatings, and plastics. The difference is that this cosmic version was far more chaotic in its composition, a much more random tangle of molecules than anything we deliberately manufacture. Studying it was painstaking work. A team at NASA's Ames Research Center shaved the material down to slivers thinner than a human hair, then turned to electron microscopy and X-ray spectroscopy to map out its chemical makeup. What they found was that this peculiar substance had been laid down in delicate layers, coating grains of ice and minerals inside the asteroid like sediment built up over unimaginable spans of time. So why does a clump of space gum matter? Because complex molecules like these may be exactly the kind of precursors that help kickstart the chemistry of life. Finding them on an asteroid, far from any planet, is the sort of result origin of life researchers describe as gold dust, direct evidence that the early solar system was busy assembling intricate organic structures all on its own. But here's where that detail I asked you to hold on to finally pays off. These molecular structures are fragile, so delicate that they would simply not have survived the searing heat of atmospheric re-entry. Had they been part of a meteorite that fell to Earth on its own, they'd have been cooked away to nothing long before anyone could study them. The only reason we even know they exist is because OSIRIS-REx collected its sample so gently and sealed it away untouched. This is the title made literal. Material this fragile, by every rule of how rocks normally reach us, shouldn't have made it to a laboratory intact. And yet, thanks to that careful, feather-light touch on Bennu's surface, it did. There was one more thread running through everything scientists pulled from Bennu, and it pointed to something almost unbelievable for such a tiny, barren world: water. Not liquid water, of course. Bennu has none today, but the unmistakable chemical fingerprints of water that once was. The sample was dominated by hydrated clay minerals, the kind that only form when rock interacts with water, confirming what earlier spectroscopic surveys had hinted at from a distance. And the deeper they looked, the more the evidence stacked up. They found serpentine, a mineral that on Earth forms at our mid-ocean ridges, where molten rock from the mantle rises up and meets seawater. They found pyrrhotite, an iron sulfide that forms here near hydrothermal vents. And perhaps most strikingly, they found water-soluble phosphates, a substance essential to DNA and to life as we know it. Put it all together, and a remarkable picture emerges. As planetary scientist Sarah Russell of London's Natural History Museum noted, the sample is so dominated by these water-altered minerals that Bennu was almost certainly never a lone, isolated rock. Instead, it seems to be a fragment of something far larger. Geologist Harold Connolly, a sample scientist on the mission, has suggested that the evidence of warm water acting over time means Bennu's parent body was at least 10 kilometers across, possibly much more, a water-soaked mud ball, or even a small world with active geology that broke apart long ago. It's extraordinary to imagine that this little asteroid might be the shattered remnant of something that once shared features with the primitive Earth, or with the icy ocean moons we marvel at today, like Enceladus or Europa. But before we let our imaginations run too far, it's worth stepping back. The presence of these ingredients doesn't mean life ever stirred there. The truth is, the building blocks we've been celebrating are remarkably common across the cosmos. Astronomers have found organic compounds in meteorites, on distant moons, drifting in nebulae, and even in the empty stretches of interstellar space. That's because all it really takes to build them is oxygen, carbon, and nitrogen, which happen to be the third, fourth, and fifth most abundant elements in the entire universe. These were forged inside stars and scattered everywhere when those stars died. We are, quite literally, made of star stuff, and from what Bennu has shown us, the stuff of life is everywhere. The astronomer Carl Sagan once compared the emergence of life to a piece of music. The organic compounds in a sample like Bennu's, he might say, are a scattering of individual notes, all the right notes, perhaps, but not yet arranged into a melody. Finding them doesn't mean the music ever played. What it does tell us is that the notes themselves are abundant, lying ready across the solar system, waiting for the right conditions to bring them together. And on a cold, airless asteroid swinging between -73 degrees Celsius and a scorching 116 degrees Celsius, those conditions simply never came. So what does it all add up to? In nearly every way that mattered, the initial analysis of Bennu's sample didn't just meet expectations, it shattered them. Supernova dust in startling quantities, amino acids, the letters of our genetic code, sugars never before seen in space, a strange polymer that shouldn't have survived the journey, and the ghostly chemistry of a long-vanished ocean. And we've barely begun. More than 200 scientists at labs around the world are still working through their share, while over 70% of the material has been deliberately set aside, preserved untouched for future generations and instruments we haven't even invented yet. The secrets of Bennu will be unfolding for decades to come. As for the spacecraft itself, its story isn't over either. Just minutes after dropping off its capsule, it fired its engines and became OSIRIS-REx, now racing towards another asteroid, Apophis, for an 18-month survey beginning in 2029. I, for one, can't wait to see what other secrets Bennu and Apophis still have to reveal. Thanks for watching, and I'll see you next time.